Hello everyone, I'm Vishal Sarveswaran, metric number S70127, and today I would like to present QFZ3123, Nanomaterial Physics, topic of electronics and optical properties of nanomaterial, where I will be focusing on the subtopic Plasmonics and Surface-Enhanced Raman Spectroscopy. First and foremost, I would like to explain what is plasmonics. Plasmonics is defined as a study of how light interacts with free electrons on a metal surface. Such key phenomena are surface plasmon resonance, SPR. And how does it occur? It occurs when light is excited collectively oscillation of electrons on a nanostructured material. So it's able to produce this intense localized electromagnetic field. And next, Raman spectroscopy. What are the functions of Raman spectroscopy? So this Raman spectroscopy are used to identify molecules based on vibrational models. It uses this inelastic scattering of light where it naturally has this weak signal, which limiting sensitivity. Next, what is surface-enhanced Raman spectroscopy? Surface-enhanced. Surface-enhanced Raman spectroscopy amplifies weak Raman signals using plasmonics nanostructure, where it can enhance these Raman signals by 10 to the power of 6 to 10 to the power of 10 times. This, I will explain on the mechanism of surface-enhanced Raman spectroscopy. First of all, electromagnetic mechanism, which is one of the dominant mechanisms it upholds, where it incident lights that excites the surface plasmons on metal nanoparticle, which creates this strong localized electromagnetic field. So these molecules that are near in these hot spots, due to this exciting of these plasmons, experience a much higher Raman scattering. Next, one of the secondary mechanism is called a chemical mechanism, where it involves a large change of a transfer between the metal surface and an adsorbed molecule. So it alters the molecule's polarizability by further enhancing the Raman signal. So the final outcome will be a very stronger, more detectable Raman signal even from a single molecules. Last but not least, I will move on to the applications, the benefits, and the challenges of this surface-enhanced Raman spectroscopy. First of all, the application of this surface-enhanced Raman spectroscopy. It's used for medical diagnostics, chemical sensing, food safety and environmental monitoring, as well as single molecular detection. When you look into the advantages, it has this they are very ultra sensitive, they are fast and non-destructive, where it can be very much portable and field deployable. It can be used in multiple fields. When we look into challenges, we're able to see that it's quite difficult to fabricate a uniform and a reproducible substrates. It has a single variability due to this inconsistent hotspots distribution due to this electron excitements, as well as the interpretation can be very much complex when it comes to real examples.
Hello, my name is Webin and my metric number is S71880, and I will be presenting on the band structures and energy levels. Energy levels can be represented as a fixed distance from the nucleus of an atom to the region where electrons can be found. Electrons can only stay in the energy level but not in the space between the energy level, as shown in the staircase figure below. This figure below shows the first 4 energy levels of an atom. The first energy level of an atom has the least amount of energy, while the highest energy level have a higher energy level, vice versa. And a fixed and discrete amount of energy is needed for the electrons to jump from a lower energy level to a higher energy level. Orbital is a region where electrons are most likely to be found. Each energy level has a specific number of orbitals correspond to the number of possible sub-levels. Electrons occupy discrete orbitals in an atom, and when many atoms bond together, their orbitals and energy levels will overlap, thus forming an energy band. Next, band structure describes how electrons occupy energy levels in a solid. And there are 4 regions in a band structure, which is valence band, conduction band, band gap, and also Fermi level. Valence band is the highest field energy band, and conduction band is the lowest empty band, where electrons can move freely. Band gap is the energy gap between valence and conduction band, and there are no electrons in this region. Band structure is important for us to determine the electronic properties and also the optical properties of a material. That's all from me.
Carrier transfer is the movement of electrons and the hole in the materials. In nanomaterials, it will differ from the bulk due to the size confinement, high surface to volume ratios, and the quantum effect. There are 2 charge carriers that can found in the nanomaterials, which are electrons and the holes. Electrons are the negative particles in the conduction band, while the hole is the positive quasi-particles in the valence band. Now let us explore the theoretical model used to describe this phenomenon. For the Duke model is to treat the electron as classical particles that move through materials and are scattered by impurities or vibrations in the lattice, known as phonons. And this is one of the earliest models used to describe the electrical conductivities in the metals. For the drift diffusions is combined the drift due to the electric fields and the diffusions due to the concentration gradient. The third one is the Landon-Bartels models, which describe the conductance as a transition problems. For the Hoping transport, the electrons are considered to move from one localized energy state to another, especially in the disorder of atmospheric material. It is a good way to describe the charge movement in organic semiconductor and some polymers. For the percolation models, it focuses on how the conductive path form in a mostly insulating matrix. It helps to explain the electrical conductivity in composite materials where the conductive filaments from random but connected network. For the ballistic transport, this model describes the carrier moving without collisions, no scattering at all over a long distance. Now I'm going to explain about the material carrier behavior. There are four types of nanomaterials. Quantum dots, 0D. It has characteristic discrete energy level, and it will transfer through hooping or tunneling between the dots. The nanowires is known as 1D, which has high aspect ratios. It will transport through the baristic or quasi-baristics. Then the third one is 2D, which is known as thin film, which is a layer materials like graphite. But in this types, it has high mobilities. Example, the graphite has 200,000 cm squared per Vs at room temperatures. Then for the last one is nanocomposite, which is a mixture of nanofiller in the polymer matrix, and it will transport dominated by percolations and interface resistance. There are several factors that were influencing the carrier transport as listed at below. The first one is the size and shapes. The nanomaterials which have smaller size will have strong confinements which can alter the band structures. The surface stage is trap the carriers and reduce the mobility. The defects and the impurities act as the scattering centers. The temperature will affect the phonons scatterings.
Luminescence, or known as cold light, was introduced by German physicist Erhard Wedemann in the emissions of light by a substance without significant heat, unlike incandescence, which require high temperatures, occur when electron absorb energy and release it as a visible light upon returning to a lower energy state. Triggered by photon absorptions, chemical or biochemical reactions, radiations, or mechanical stress on crystal. The color or wavelength of emitted light depends on the material, not on the type of energy used to excite it, where the law of luminescence is the emitted light always has a longer wavelength than the exciting radiations. Material emitting luminescence are called luminophore or phospho. Luminescence process. At A, electron in lowest energy state, ground state. At B, electron absorb energy and move to excited state S1 or higher. At C, electron returns to a lower energy state emitting a protons or light. Photoluminescence mechanism. Light emissions occur when an electron in a nanomaterial transitions from a higher to a lower energy state, release a photon. The wavelength of emitted light is determined by the band gap, which can be tuned by changing nanoparticle size and compositions. There are two main types: fluorescence emissions from a singlet excited state S1 to S0, typically fast in nanoseconds. Phosphorescence emissions from triplet state T1 to S0, typically slower, microseconds to seconds. Chauvelin diagram showing absorptions, realizations, and emission step, with the photon emission shown in a short wavelength blue in the diagram occur between states of the same spin state. This is termed fluorescence. If the spin state of the initial and final energy level are different, the emission is called phosphorescence, shown in longer wavelength red. If fluorescence is statistically much more likely than phosphorescence, the lifetime of fluorescence states are very short, and phosphorescence somewhat longer, 1 multiplied to 10 powers of -4 second to minutes or even hour. Think about glow in the dark flying disc. Energy transfer mechanism is the movement of excitations energy from one species to another without emissions of a photon. There are two types of mechanisms, which are Foster resonance energy transfer, FRET, and Dexter energy transfer. FRET is a non-reactive energy transfer process that occurs between a donor and acceptor species, typically within 1 to 10 nanometers of each other. It relies on dipole-dipole interactions and requires spectral overlap between the donor emissions and acceptor absorption. FRET is highly distance dependent, making it a powerful tool for probing nanoscale interactions and optimizing luminescence in nanomaterial. The mechanism is widely used in biological sensing, imaging, and the designs of fluorescence probe due to its ability to monitor molecular interactions at the nanoscale. FRET fundamental. At A, excited donor transfers its energy by a non-radiative process to a nearby acceptor, causing it to emit fluorophoresis. The distance between fluorophores should not exceed 10 nanometer. At P, the donor emission peak must overlap with the acceptor excitation spectrum. The grey area corresponds to the overlap region. At C, efficiency as the function of the distance between donor and acceptor fluorophores RDA. The excited energy transfer, also called an electron exchange energy transfer, is a photophysical mechanism where a line exchange of electrons occurs between donors and acceptor molecules. In the excited energy transfer, an electron is transferred from the HMSO mole of the donor in the excited state to a LUMOR of the acceptor in its ground state, while the electron is transferred from the HOMO of the acceptor to the SSO more of the donor. At the end of the process, the acceptor molecules become excited and the donor is deactive. In contrast to FRET, which is singlet-only process, in the excited energy transfer, both singlet and triple energy transfer can occur. Energy transfer processes such as FRET and Dexter transfer are vital for optimizing luminescence efficiency and enabling color manipulations in nanomaterial. In the night doped system, carefully engineered energy transfer cascade allow for a full spectrum emission for a single citations wavelength, significantly enhance the performance of lighting display technologies and sensors. By managing donor acceptor distance and energy level alignment, researchers can fine-tune emissions intensity and wavelength, improving device efficiency and functionality.